Okay, so we're going to get into Chapter 8 now, and the topic of Chapter 8 is gases. So we're going to set a foundation for our discussion of gases by discussing the kinetic molecular theory of gases. And I have a hard time saying this, so I'm going to avoid saying it a lot because if I start it, you'll see I'm going to slip up. So I'm just going to say, let's say Km. I'm going to talk about the kinetic molecular theory, Km. All right, and let me make my markers the right size here. All right, so the Km theory has sort of 5 principles that we're going to appreciate. Number 1 is that particles, gas particles, move randomly. They move randomly and with high velocities. Okay, that's point number 1. So let each of these represent a gas particle. Obviously, gas particles are much, much smaller than this, but we make them big so you can see them. What they're doing is they're moving very randomly and at high velocities. The second principle is that they have very small attractive or repulsive forces between the molecules. In other words, they do not attract each other and they do not repel each other. Very, very small attractive or repulsive forces. The third principle is that they occupy a much larger volume than the volume of the molecules themselves. And what I mean by that is that this particle is very small, and we're going to say it's so small that its volume is approximately 0. Okay, the volume of the particle is approximately 0, so that the volume of the total volume that the gas probes or occupies is not made of particles, it's made of empty space. Okay, number 4, that the particles are in constant motion and they're moving rapidly in straight lines until they hit something. So you can see this orange thing, it hit that green particle. Can you see that? It's coming along here and bam, hits the green particle, bounces off, hits the top, and comes over here, okay? So they move in straight lines until they hit something else. And then the fifth principle is that Kelvin temperature is proportionate to the average kinetic energy of the molecules. The kinetic energy is essentially a measure of Kelvin temperatures. All right, so let's talk about now the properties that describe a gas. They are pressure, volume, temperature, and amount. Pressure, volume, temperature, and amount. The pressure is the force exerted by the gas in the walls of the container. The volume is easier to understand. It's the space occupied by the gas. The temperature is the determining factor for the kinetic energy of the particles, how fast they're going. And the amount is essentially, that's also easy to appreciate. It's just amount of gas that you have present. We're usually going to measure amount in terms of moles. We're going to measure temperature typically in terms of kelvins. Volume, we're going to use liters or milliliters, both of those equally. And atmosphere or pressures, we're going to typically go with atmospheres, although it's not uncommon to use millimeters of mercury or torrs. The SI unit is pascals, but the most common ones are going to be atmospheres and torrs. Okay, so let's look at each of these individually. First of all, the volume. The volume of a gas is the same as the container that it occupies because the gas particles all go all around hitting the walls, okay? So would you say the volume of a gas is always defined by the volume of the container that it occupies? It's usually measured in liters or milliliters, and we'll probe this a little bit more later. Increases with temperature at a constant pressure. Okay, temperature now is the second one I want to talk about, and the temperature relates to the average kinetic energy of the molecules, and we're going to use temperature as kelvins. When the temperature of a gas is decreased, the molecules have fewer collisions. When it's increased, it has more collisions. All right. The third thing the third property is pressure, and pressure is a measure of the gas of particle collisions against the size of the container. And it's measured typically in units of atmospheres. We are going to use millimeters of mercury and torr a lot. Those are the same thing. Pascals is the SI unit, and much less commonly we're going to say PSI, or pounds per square inch. Gas particles in the air exert pressure on us, and we call that atmospheric pressure. So this is this guy standing here with a sweater over his shoulders, standing here on the Earth in the atmosphere. The atmospheric pressure is the pressure that a column above his head pushes down on him. And it's the same in all directions. This pressure is the same as that pressure is the same as that pressure. That's atmospheric pressure. It's the gas particles in the air exert on your body. Okay, I think I'm going to skip the diagram of the barometer, and let's go with the units of pressure. The units of pressure are typically atmospheres, okay? The abbreviation is atmospheres. And if we're going to convert to atmospheres, it's going to be, well, exactly 1. Now, millimeters of mercury, we're going to, the abbreviation we use is that, and there are 760 millimeters of mercury in 1 atmosphere. Torr is the same thing as millimeters of mercury. There are 760 torr in 1 atmosphere. I don't want to care about that. Inches of mercury we don't see very often. Pounds per square inch we don't see very often, but if you're going to put some air in your tire at the gas station, you're probably going to put something like 30 pounds per square inch or 40 pounds per square inch. And that pounds per square inch is 14.7 pounds per square inch in 1 atmosphere. Pascals is the SI unit. We call it PA, and there's 101,000 pascals in 1 atmosphere. All right, atmospheric pressure is different on top of a mountain than it is at sea level because there's a smaller column of air pushing down on the top of the mountain than there is than the one that goes all the way to the sea level, right? So we'll give you some pressures here in this next table. The pressure at sea level, its altitude is 0 and its pressure is 760 millimeters of mercury. At Los Angeles, which has a slight elevation, very little, it's basically there by the sea, right? There's ocean by LA. Its atmospheric pressure is slightly higher, or rather slightly lower because it's slightly higher in elevation. Denver, which is pretty high, right? It's about a mile high, and its atmospheric pressure is 630 millimeters of mercury. The Dead Sea, which is actually lower than sea level, amazingly, has a higher pressure than atmospheric pressure. And Mount Everest, which is really high, right, 9 kilometers high, that has an atmospheric pressure of 253. Really hard to breathe up there. All right, so let's look at a learning check. And I'm gonna ask you to pause the video and then calculate these 2 questions, and then come back and check my math. Okay, so I'm gonna suppose you paused it, and the question is, if I have this much millimeters of mercury, right, how many atmospheres am I gonna have? And so we're gonna just do a conversion with the picket fence method. You've seen this before. Millimeters of mercury. There's 1 atmosphere for 760 millimeters of mercury. And so if I have 475 millimeters of mercury, right? Millimeters of mercury cross off, I'm left with atmospheres. 475 over 760 is not 475, so it can't be A. 475 over 760 is a small number. It's less than 1, so it can't be 300,000, which is what that number is, right? So it has to be B, right? I won't even calculate that in the calculator. All right, so let's do the second one, which presumably you've already done. You paused the video and looked at it. They're asking, if you have 2 atmospheres, what's the pressure in millimeters of mercury? All right, we set it up like this, millimeters of mercury. I was given atmospheres, and I know that there's 1 atmosphere for every 760 millimeters of mercury. And so if we're asking for 2 atmospheres, right, atmospheres cross off, and I'm left with millimeters of mercury. 2 times 760 is not 2. 2 times 760 is about that. I guess that's right, right? B. Okay. All right, so I think that's all we're going to do. This last learning check is not, I think, is valuable. So let's stop the video here, and hopefully that's a good exposure into the properties of gases, kinetic molecular theory of gases, and some conversions.